Now we will study the new concept, that is torque on a current loop, and also we study magnetic dipole. Now in the previous class we have studied the force experienced on a current carrying conductor. Now what is that expression? Now the force experienced by a current carrying conductor is given by ILB sin theta, that we know. I is the current flowing through the conductor, L length of the conductor, B is the external magnetic field, and theta here is, it is the angle between the current element and the field vector. Okay. Now based on that one, now in this concept we are going to study, we are taking a rectangular loop through which a current I is flowing. Now that rectangular loop is placed in an external magnetic field provided by the two magnets N and S. Now how this current carrying rectangular loop behaves in the presence of external magnetic field, that we are going to study today. For that one, consider a rectangular loop ABCD as shown in the diagram. It is placed between two horseshoe magnets having the poles N and S, which are providing a uniform external magnetic field. The ends of the rectangular loop are connected to a carbon brush, which in turn is connected to a battery. Now that battery obviously supplies a current through the rectangular loop. Now this is an arrangement. Now first we have placed the rectangular loop so that its plane is parallel to the field direction. The magnetic field is from north towards the south. Now the direction of the magnetic field here it is as shown here. This is the magnetic field direction. Okay, and the current direction in various segments of the rectangular loop are also as shown in the figure. Now when the plane of the rectangular loop is parallel to the field direction, first case. Now what happens? As and when the current starts to flow through the rectangular loop, because of the presence of the magnetic field, the various segments of the rectangular loop experiences force. Now see there, the segment AD and the segment BC, look here, the segments AD and BC, they are parallel to what? The magnetic field. Since the lengths of the segments AD and BC are parallel, now here strictly speaking BC becomes parallel because current is flowing from B to C and the magnetic field is also along the BC direction, therefore it is parallel. In the case of AD section, the length segment and the field are anti-parallel. Okay, either it is parallel or anti-parallel. Now what is the angle? Now for the parallel case, angle theta is equal to 0. For the anti-parallel case, the angle theta is 180 degree. Then obviously what is sin theta? Then sin theta term becomes 0. Therefore the force experienced by these two segments, that is AD and BC, is 0. That means since these two segments are parallel to the field direction, they will not experience any force. Okay. Now come to the next segment, that is AB. I am taking the segment AB. For the segment AB, now the current is flowing from A to B as shown in the diagram. The field is perpendicular to the length of that segment. Therefore obviously what is theta is 90 degree. Then obviously sin theta becomes 1. Sin theta becomes 1. Since these two are perpendicular, the segment AB experiences a maximum magnetic force. It experiences a force. Now the direction of the force on the segment AB, if you use the left hand rule, showing the forefinger shows the direction of the magnetic field, middle finger shows the direction of the current, then the thumb shows or gives the direction of the magnetic force experienced. Now look here, the current is in this direction, the middle finger, current is here, and the magnetic field is along this direction. Magnetic field is along this direction. I will stand here. Now current is into the plane of the board. The magnetic field is from N to magnetic force. So therefore the segment AB experiences a magnetic force that is downwards. It experiences the force downwards. Then what is the magnitude of that force? Now that magnitude of the force is given by the simple relation. The general formula is this one, ILB sin theta. Now I, that is the current flowing through that segment. L is length. Now here we have taken length as B. In this diagram we have taken length as B and breadth as A. A rectangular loop of length B and breadth A. Okay. So therefore it becomes B. And the magnetic field is capital B. And obviously sin theta is 1. Now this is the magnitude of the force experienced by the segment AB. And I will denote it as F1. Now what is the direction of this force? It is acting downwards. Clear? Now take the segment CD. Let me choose the segment CD. Now in this segment the current is flowing from C to D and the magnetic field is perpendicular to it. Obviously angle is 90 degree, therefore sin 90 becomes 1 and hence the segment CD also experiences maximum force. The magnitude of the force, once again I will write it as F2. If I write it as F2, once again it becomes the same I, B, B. Now in place of L we are writing the length of that particular segment, that we have taken it as B. Therefore it is. Now look here, then what is the direction of this force? Now we have to find out the direction. Now the current is coming out of the plane of the board. Now current is coming out of the plane of the board. The magnetic field, obviously it is from N to S direction, magnetic field. Then the extended thumb indicates the direction of the force experienced by that segment. It is upwards in this case. So therefore the segment CD experiences a force in the upward direction. Now here we have an F1 force, it is the downward direction and it is experiencing a force. So segment CD is experiencing a force in the upward direction. Now these two forces are equal and opposite. But these two forces are not acting at the same line of action. They are not collinear. Net force is 0. Since they are not at all acting at the same point or they are not collinear, they constitute a couple or the rotational effect, or we call it as torque. Now this torque tends to rotate the rectangular loop. Now in this case it is rotating in the anti-clockwise direction. Now these two forces are equal in magnitude but opposite in direction. They are equal in magnitude but opposite in direction. Therefore they experiences a torque, the rotational effect caused by the two forces. Therefore torque is given by Since we have taken this as the midpoint, if I consider this as a midpoint, for the segment AB, now force is, it is F1 into, now it is half of the breadth, that is A by 2. Torque is, it is the product of force and the perpendicular distance from the axis of rotation to that segment. Therefore, it is F1 plus A by 2 plus, on the second force also, it is producing a torque, that is F2 A by 2. Now, this is the torque on the segment AB. Now, this is the torque on the segment CD. Therefore, total torque is the sum of those two. Therefore, torque is equal to, now substituting for the force, IBB into A by 2 plus, here also IBB into A by 2. If you add them, I will get torque is equal to IBB A by 2 plus A by 2, it becomes A. So therefore, torque experienced by the rectangular loop, I will rearrange the terms here into, I will combine A and B. Now look here carefully, what is A? It is the breadth of the loop. What is B? It is the length of the loop. Their product is obviously the area of the rectangular loop. Therefore, now torque is equal to I into B into A, where A is equal to, so A into B, it is the area of that current carrying rectangular loop. Therefore, torque tau is equal to B into I into A. Now, I into A, it is the product of current and the area of the current loop. Now, that is denoted by one more quantity, that is M. Now, M is called magnetic moment. M here, M is called as magnetic moment. So therefore, it is a vector quantity. It is the product of current into area vector. Magnetic moment is also a vector quantity, but its direction is once again given by the right hand rule. Now this current loop possesses a magnetic moment. Where is the direction of that magnetic moment? That is given by the right hand rule. Now if you curl the four fingers indicating the direction of current flow in the loop, in the rectangular loop here, the current is flowing from A, B, C, D. Therefore, I am curling these four fingers along that rectangular loop. Then obviously in this diagram, the extended thumb is downwards. That indicates the direction of the magnetic moment. Now here, the direction of the magnetic moment is downwards. Okay. So for the clockwise rotation of the current, the magnetic moment is into the plane of the board. Magnetic moment is into the plane of the board. For the anti-clockwise rotation, the magnetic moment is coming out of the plane of the board. Magnetic moment is coming out of the plane of the board. Now that notation is similar to that of magnetic field. If the field is into, this notation we are using. If the field is coming out, we are using this notation. In the similar way, the magnetic moment can also be represented like that. Now, this is one case. Now, what happens if initially this plane is rotated through a certain angle? That means the plane of the rectangular loop is not coinciding, or it is not parallel to the magnetic field direction. It is making a certain initial angle theta. If it makes a certain initial angle theta, then what is the torque? Then obviously we are going to obtain the torque in the same manner. In that case, now torque is equal to, the force will be the same, into A by 2 along with sin theta. We are getting along with sin theta. That I will show here. So initially, this is the magnetic field. Now perpendicular to it is a magnetic moment. Now this angle is theta. That angle is taken as theta. Now here we are having the force F1. Now here we are having the second force F2. Okay. Now what is this? Obviously, since it is theta, what is this distance? So therefore, torque is equal to F1 A by 2 sin theta plus F2 A by 2 sin theta. Now substituting for F1, IB B A by 2 sin theta plus IB B A by 2 sin theta we are getting. So if you add them, you will get I B A by 2 plus A by 2, it becomes A into sin theta. Therefore, torque is equal to, I will rearrange the terms, B into A is nothing but the area vector into sin theta. Therefore, torque is equal to B into I into A, as I have said earlier. We are combining the current and the area vector. Now what is that one that I have mentioned? It is m sin theta. Since torque is depending on the angle, therefore in vector form we can write torque is equal to m cross b. Since the presence of the sin theta term, this torque is nothing but the vector product of magnetic moment and the field vector. Now this torque is similar to that of a torque experienced by an electric dipole. That is given by, now this is similar to that of electric dipole. So that is torque experienced is tau is equal to P cross E. So P is the dipole moment, electric dipole moment, and E is the electric field. Now this is in comparison with the electricity and magnetism. So therefore, the rectangular loop experiences a torque which is the cross product of magnetic moment vector and the field vector. Obviously direction, it is perpendicular to the plane containing the two vectors. Here we have defined a new quantity, magnetic moment. M is equal to is I into A. It is the product of current multiplied by the area of the current loop. Now what is the dimension of this one? Now dimension becomes, now for the current it is ampere, area it is L square. Therefore the dimensions of magnetic moment is equal to A into L to the power of 2. Then what is the SI unit of magnetic moment? So obviously current is ampere and this one is meter square. Ampere meter square is the SI unit of magnetic moment. Okay. Now the torque is cross product of magnetic moment and the field vector. Now when it is 0 and when it is maximum, we obviously know that if M is parallel to B, M is parallel to B, then theta is 0, therefore torque is 0. Therefore the equilibrium is stable. Stable equilibrium. Okay. If M is anti-parallel, M is anti-parallel to the magnetic field, that is theta is equal to 180 degree, then the equilibrium is unstable. So here carefully look here, M is parallel to B. What is that meaning? The plane of the loop is perpendicular to the field. Don't get confused from here onwards. Now obviously the direction of the magnetic moment is always perpendicular to the plane of the loop. Now here M is parallel to B or anti-parallel. That represents the state of equilibrium. If M is parallel to B, that equilibrium is stable. If M is anti-parallel to B, that equilibrium is unstable. Now in this case, if you have given a small rotation, in the case of unstable, it tends to rotate further and bring back to its original position. Now here carefully remember, M is parallel means the plane of the loop, rectangular loop, is perpendicular to the field direction. M is parallel or anti-parallel anta helidre, plane of the loop, ee diagram alli torisiro prakara plane of the loop parallel idane. Ee case alli magnetic moment, look here, the magnetic moment and the field are 90 degree each other. E position alli that rectangular loop experiences a maximum torque. Clear? ಹಾಗೆ ರೊಟೇಟ್ ಆಗಿ 90 ಡಿಗ್ರಿ ಹಿಂಗ್ ಬಂತು ಹೇಳಾದ್ರೆ ಆ ಕೇಸಲ್ಲಿ ಏನಾಗ್ತದೆ, ಮ್ಯಾಗ್ನೆಟಿಕ್ ಮೊಮೆಂಟ್ ಫೀಲ್ಡ್ ಪ್ಯಾರಲಲ್ ಅಥವಾ ಆಂಟಿ ಪ್ಯಾರಲಲ್ ಆಗ್ತದೆ. ಇನ್ ದಟ್ ಕೇಸ್ ಇಟ್ ವಿಲ್ ನಾಟ್ ಎಕ್ಸ್ಪೀರಿಯನ್ಸಸ್ ದ ಟಾರ್ಕ್ ಅನ್ನು ಎಕ್ಸ್ಪೀರಿಯನ್ಸ್ ಆಗಲ್ಲ, ಟಾರ್ಕ್ 0 ಆಗಿ ಹೋಗ್ತಾನೆ. ದಟ್ ರೆಪ್ರೆಸೆಂಟ್ಸ್ ದ ಸ್ಟೇಟ್ ಆಫ್ ಈಕ್ವಿಲಿಬ್ರಿಯಂ ಅಂತಂದೇಳಿ ಅರ್ಥ ಮಾಡ್ಕೋಬೇಕಾಗ್ತದೆ. ಓಕೆ, ಸೊ ನೆಕ್ಸ್ಟ್, if that rectangular loop is having capital N number of turns, if it is having a capital N number of turns, then what is the magnetic moment of that loop? Then obviously the magnetic moment is given by N into I into A, magnitude of the magnetic moment. If the coil is having N number of turns, that is given by this simple relation. One more thing, initially the plane of the loop is making a certain angle theta. In that case, the segment BC and AD, they also experiences force. In the first case, they will not experience force. F is 0 in both the cases. But whenever the plane of the loop is making a certain angle theta with the field direction, then the segments BC and AD are also experiencing a force, but those two forces are equal and opposite, and their line of action is along the axis of rotation, and hence those two forces cancels. Only the force experienced by the segment AB and CD constitutes the torque. Now we will study the next concept of circular current loop as a magnetic dipole. Now look at the diagram that we have already studied. We have a current carrying a circular loop and we have derived the expression for magnetic field at an axial point due to that current loop. Now this is a current loop of radius capital R, and we have chosen the axis passing through the center of that circular loop. And if I take any point P and that axis which is at a distance x from the center, obviously that point P is at a distance small r from any point on the circumference of that circular loop, or the current element that we have studied, and we have derived the expression for that magnetic field. Now what is the expression for that magnetic field? We have obtained the magnetic field due to the entire circular loop along any axial point P is given by mu naught I r square divided by 2 into r square plus x square to the power of 3 by 2, that we have already derived. Now here what is I? Current flowing through that circular loop. capital R, the radius, x, the distance of the axial point from the center of the circular loop that we have studied. Okay. Now, we will make an assumption. The point P is at a very larger distance compared to the radius of the circular loop. That means x is very much greater than r. In that situation, we are neglecting r square term only in the denominator. If that is the case, then what will becomes mu naught I r square divided by 2 into, now here we are neglecting r square term since x square is very much greater than compared to that of r square. So therefore we are getting x square to the power of 3 by 2, 2 get cancelled, therefore we are getting x cube. Okay. Now multiplying both the numerator and the denominator by pi, I will get mu naught I pi r square divided by 2 pi x cube. Just I am multiplying, dividing by pi. Okay. Now what is pi r square? Obviously it becomes, since r is the radius of the circular loop, pi r square is the area of the loop, circular loop, mu naught I a divided by 2 pi x cube, where a is equal to pi r square, pi capital R square is area of that circular loop. Okay. Now we have obtained here the current multiplied by the area. What is that one? That is the magnetic moment that we have studied earlier. Therefore, B is equal to mu naught m divided by 2 pi x cube. So here what is m? It is equal to product of I into A is magnetic moment. Magnetic moment of that particular loop, that is circular loop, magnetic moment of the circular loop. So therefore, the magnetic field along the axial point, I will rearrange the terms. I am multiplying both the numerator and denominator by 2. Therefore, I am getting 2m. Here we are having m. Multiplying by 2, I am getting 2m. Now 2 pi into 2, it is 4 pi into x cube. Now look at this expression carefully. We are getting B is equal to mu naught divided by 4 pi 2m by x cube. This is the expression for the magnetic field in the case of a circular loop. Now this relation is similar to that of this one. Look here, the electric field is equal to 1 divided by 4 pi epsilon naught into 2p divided by r cube. Now this is the expression for the electric field due to an electric dipole along the axial point. In the same manner, this is the expression for the magnetic field along the axial point due to a current loop. In analogy with this one, we can say that a current carrying circular loop at a larger distance looks like a magnetic dipole. It looks like a magnetic dipole. So here mu naught epsilon naught is replaced by mu naught and electric dipole moment P is replaced by the magnetic dipole moment. These are the two changes we are having. So therefore, this represents the field due to magnetic dipole. Magnetic dipole. Therefore, a current carrying circular loop or any planar loop, even not only the circular, any planar loop, it behaves as a magnetic dipole at a larger distances. Okay. Now, electric dipole is made of two elementary units. Those are charges. But magnetic dipole is made of a current loop. It is a current loop. Is there any existence of monopole? monomagnetic pole? No, there is no existence of monopole in the case of magnetism, but there is an existence of a single charge in the case of electrostatics. But in magnetism, we are having dipole, not a monopole. Now we will study the next concept, magnetic dipole moment of a revolving electron. That means we have an atom consisting of a central positively charged nucleus around which electrons are revolving in their particular orbit as shown in the diagram. Since the electron is having a charge, it possesses an electric current and hence it has a magnetic moment. That we call it as magnetic dipole moment of a revolving electron. Now what is the expression for that magnetic dipole moment of the electron that we are going to work out? It is a very simple expression. Okay. For that one, consider an atom having a central nucleus of charge plus Ze as shown in the figure. An electron of charge minus E is revolving around it. Now in this diagram we have taken electron is revolving in the anti-clockwise direction. Since electron is flowing, obviously there is a current produced in the opposite direction to the flow of electron. Now what is the current now? Therefore the current I is given by charge divided by the time taken. So here time taken is time taken for one revolution we have taken. Now what is the direction of this current? Since the electron is revolving in the anti-clockwise direction, the direction of the conventional current is obviously in the clockwise direction. It is in the clockwise direction. So therefore I is equal to E by T. Now what is T? It is time period of revolution. Now consider the electron is revolving in a circular orbit of radius r with an orbital velocity v. V is the orbital velocity. Then by the definition of velocity we have it is the distance traversed divided by the time taken. That is here capital T, time taken. RT is equal to, now what is the total distance traversed here? It is nothing but the circumference of the circle, that is 2 pi r divided by, now velocity, it is v. Now substituting this in this above expression, I will get current I is equal to, so E into V, E divided by T is 2 pi r divided by V, or that is equal to E into V divided by 2 pi r. Okay. Now this is the expression for the current produced by a revolving electron. Now since there is a current, that electron possesses a magnetic moment. Now here that magnetic moment is denoted by the letter mu L because it is the orbital magnetic moment. In the earlier we have mentioned magnetic moment as M. For the case of an electron here, since it is orbiting, therefore orbiting magnetic moment is denoted by the letter mu L, which is nothing but just the product of the current produced by the electron and the area of that current loop. Here what is that current loop? It is a circular orbit, a circle of radius r. If you multiply those two, we will get the magnetic moment of the revolving electron. So therefore that is equal to I, we have given this relation, that is E V divided by 2 pi r into. Now what is the area of that circular loop? It is pi r square. Okay. So therefore mu L is equal to, now pi get cancels, 1 R get cancels. Therefore, I am getting E V R divided by 2. Okay. Now, what is the direction of this magnetic moment? Now we are working out direction. Now the direction is given by the right hand rule. Carefully look here. The electron is revolving in the anti-clockwise direction. Therefore, obviously the current is in the clockwise direction. Now, if you hold the right hand so that the current is in the clockwise direction, then the extended thumb is into the plane of the board. That means the magnetic moment of the revolving electron in this case is into the plane of the board, that is represented as shown here. Clear? But electron is revolving in the anti-clockwise direction. If you look at the angular momentum by the same right hand rule, it is coming out of the plane of the board. Orbital angular momentum of the electron is coming out of the plane of the board, but magnetic moment is into the plane of the board. That we will study later onwards. Now this is the magnetic moment. Now just multiplying both the numerator and the denominator by mass of the electron, that is me. What we are going to get? Mu L is equal to charge E by 2 me into me V into R. Multiplying both the numerator and denominator by me, that is mass of the electron. Now look here, we are getting m into V into R, which is nothing but the moment of linear momentum, that is the angular momentum. Therefore, mu L is equal to E divided by 2me into, now this term is represented by the letter L, that is the orbital angular momentum, where L is equal to mvr is orbital angular momentum. It is the orbital angular momentum. This is the magnitude. If I write it in the vector form, then I will get mu L vector form is equal to, we are getting a negative sign. I will tell you why it is negative sign. Okay. A into vector L here. We are introducing the negative sign because the orbital angular momentum and the magnetic moment, dipole moment, the magnetic moment of the electron, they are in opposite direction. Very simple. Electron is revolving in the anti-clockwise direction here. Therefore, what is the direction of the angular momentum? L. If I use the right hand rule, the encircled 4 fingers indicates the motion of the electron. Then the angular momentum is coming out of the plane of the board. It is coming out of the plane of the board. L is coming out. Direction of L. But what is the magnetic moment? The magnetic moment is related with the current. Current is in the clockwise direction. Therefore, the magnetic moment is into the plane of the board. Therefore, these two are exactly opposite in direction. Therefore, that's why we are introducing the negative sign. Okay. So, in magnitude, if I write only the magnitude, therefore, mu L is equal to E L divided by 2 m. If it is a positive charge, obviously there is no meaning of negative sign. Clear? Okay. Now let me define one more quantity here, mu L divided by L. If I take that one, so that is equal to E divided by 2 into me I am getting. Now this quantity mu L by L is called gyro magnetic ratio. The ratio of magnetic moment of the revolving electron to its orbital angular momentum is called gyromagnetic ratio. If you substitute the value of the charge of the electron and mass of the electron, if you work out, I will get its value is about 8.8 into 10 to the power of 10. That is coulomb per kg. 8.8 into 10 to the power of 10 coulomb per kg. It is gyromagnetic ratio. Clear? Okay. Next, in the chapter, atomic chapter, we are going to study later onwards Bohr postulates. Bohr has given three important postulates to understand the structure of the atom. Among them, the second postulate is very, very important one. That postulate states that the electrons revolve only in those particular orbits for which the orbital angular momentum is an integral multiple of h by 2 pi. That we are going to study in the 12th chapter. The orbital angular momentum of the revolving electron is given by n into h divided by 2 pi, where n is a natural number 1, 2, 3, that is principal quantum number. We call there as principal quantum number, and obviously h is Planck's constant, that we know. Now substituting this value in the above expression for magnetic moment of the electron, we get, I will take this relation, therefore mu L is equal to E into L divided by 2 me. I am substituting for L by using Bohr postulate. Therefore, mu L is equal to E divided by 2 me into it is N h divided by 2 pi. Therefore, the magnetic moment of the revolving electron mu L is given by N E h divided by 4 pi me. That is the expression. It is the magnetic moment of the revolving electron which is revolving in any orbit. Clear? If that electron is revolving in the first orbit, if I take electron is revolving in the first orbit, then I have to choose n is equal to 1. Therefore, that is the minimum value of the magnetic moment of the electron. The minimum value of the magnetic moment of the electron is obtained when you choose n is equal to 1. So therefore, mu L minimum is equal to E into h divided by 4 pi me. Now here all are constants. If you substitute the charge of the electron and the value of the Planck's constant, that is 6.63 into 10 to the power minus 34, and mass of the electron 9.1 into 10 to the power minus 31, substituting and simplifying, we will get the minimum value of the Bohr magneton 9.27 into 10 to the power of minus 24 ampere meter square. 9.27 into 10 to the power of minus 24 ampere meter square, and this is called as Bohr magneton. The value of the magnetic moment of the orbital electron in the first orbit is called as Bohr magneton. Now that is the expression for the orbital angular magnetic moment of the revolving electron.